Good day everyone, my name is Dan Wizi and I am here to present how to produce hydrogen gases using SMR reactor. At the end of my presentation today, we are expecting to know that the type of reactions, the reactor designing, the type of the catalyst used, the strategy to maximize the selectivity and the yield, and also finally the reactor's block diagram to produce hydrogen. Let us move on to the first part. There are two types of reaction happening inside the reactor, which are steam methane reforming (SMR) and also water gas shift (WGS). In SMR reactor, there will be two parallel reactions which both consume methane and water. However, they have different products which are carbon monoxide and carbon dioxide respectively. Both reactions produces hydrogen gases, and in this case, the main reaction is reaction 1 which produces carbon monoxide. Next, in WGS reactor, there will be only one reaction, and this reaction further reacts the carbon monoxide produced in the first reactor into hydrogen and carbon dioxide. As our reactant stream flows into the reactor, we are assuming that the water is constantly supplied into the system and always in excess so that the reactions are always irreversible. Besides, the natural gas supplied into the system is treated and contains high concentration of CH4 methane, which means that the stream does not need to undergo further treatment such as desulfurization. The steam reforming or steam methane reforming (SMR) is a chemical synthesis for producing syngas such as hydrogen and carbon monoxide from hydrocarbons such as natural gas. As we mentioned above, there are two reactions in an SMR reactor, and the reaction 1 with the product carbon monoxide and hydrogen is the main reaction, while the reaction 2 is the subreaction. We obtain the pre-exponential factor value and activation energy from lab study, and the reaction rate constant K is calculated using Arrhenius equation. The products from the SMR reactor next moves on to the next stop, which is the water gas shift reactor. As we can see, there is only one reaction occurring in WGS, and it further reacts the carbon monoxide into carbon dioxide and hydrogen. This eventually increases the amount of hydrogen production and decreases the release of carbon monoxide gases. This is an important consider as carbon monoxide is more harmful towards human and the environment compared to the carbon dioxide that was produced. The pre-exponential factor and the reaction rate constant was obtained using the same method as in SMR. Water gas shift reaction is a moderately exothermic reversible reaction that is thermodynamically favored at low temperatures and kinetically favored at high temperatures. Thus, it is performed at two temperatures, which is the HTS high temperature shift and LTS low temperature shift. The reactor we choose is a tubular catalytic reactor. A tubular catalytic reactor contains a vessel through flows continuously, usually at steady state and configured so that the conversion of the chemicals and the other dependent variables are functions of position within the reactor rather than of the time. In this reactor, it contains several tube packs with a catalyst inside of it to cater for respective reaction and its reacting conditions. The advantages of a tubular catalytic reactor is it has a high efficiency, which in other words, the rate of conversion per unit catalyst mass is high. It can carry out continuous operation. It has a low operating cost and capital expenditures. It has higher efficiency when dealing with gas-phase reactions, and most importantly, it has a good heat transfer. This is very important because when excess heat was produced due to instability of catalytic reactions, it can be removed through the tube walls. There are also the disadvantages of this reactor, which are undesired thermal gradients might exist, and most importantly, the shutdown for cleaning and maintaining process is very expensive. It causes inability to replace catalyst during the production. Next, we are moving to the type of catalyst used. In SMR reactor, nickel is the mostly used metal as catalyst because of its high reactivity and low attrition. A nickel-based catalyst can withstand very high temperature and exhibits good mechanical strength. Furthermore, we are using alumina-based supporting material, as it has showed good reactivity and no agglomeration, or in other words, low mass accumulation. Actually, there are also other noble metals that are active for steam reforming. but these materials are generally too expensive to be used in conventional industry. In a nutshell, nickel-based catalyst with alumina oxide as a supporting material is the best choice of catalyst for this reactor. Next, the water-gas shift reaction. We have chosen magnesium ferrite as a catalyst for high-temperature shift reaction and iron oxide for the low-temperature shift one. Both of the catalysts can handle temperature shifts and they are able to stabilize highly reactive action. And at the same time, they are able to decrease the activation energy required by the reaction effectively. In order to maximize the selectivity or yield of the hydrogen gas, the following method can be introduced. Firstly, we can increase the reaction temperature at constant pressure in the SMR reactor. In SMR reactor, the reaction executed are all exothermic and that favors high temperature system. Next, we can decrease the pressure of the system at constant temperature. As we can observe, the number of moles of gas at the product site is higher than the reactant site in all the reactions, which in other words, by decreasing the pressure helps to shift the reaction equilibrium to the product site. Lastly, we can install a hydrogen membrane to the reactor bed. An experiment was carried out between two reactors with and without hydrogen membrane, while the temperature and pressure were set to constant. It showed that the yield of hydrogen gas is higher when a hydrogen membrane was installed. Moving on, the block diagram on how we produce hydrogen gases are as shown on the slides. Firstly, we supply methane and water which is in excess into the SMR reactor that operates at a high temperature which exceeds 700 degrees Celsius. At this phase, the nickel-based catalyst with alumina oxide as support was used in the reactor. The product of SMR reactor that contains the mixture of hydrogen, carbon monoxide, and carbon dioxide then undergoes WGS reaction in the second reactor, which includes high and low temperature shift. This process was aiming to further react the harmful carbon monoxide in the stream into hydrogen gases and less harmful carbon dioxide by large scale. The product of the second reactor then undergoes purification methods to increase its purity, which in our case are absorption and adsorption.
Hello, I am Imad Rayhan. I'm going to represent the CO2 removal unit for our integrated project. For the CO2 removal unit, we have two main unit operations, which is the absorber and the stripper. The absorber is used to purify the hydrogen gas from the CO2 using a proper amine. And then the amine, it will go to the stripper where the CO2 it will be stripped off, and the amine it will be recycled back to the absorber. For the ease of the calculations to find our unknowns, we will use a simple block flow diagram, as can be seen from the presentation. We have our main concern, which is the molar flow of the hydrogen gas. It will be represented as F1, and then the CO2 removal, it will be F4. Applying an overall mole balance, we can simply find our F1 and F4, as can be seen, for the hydrogen production and the CO2 gas. And then applying a mole balance on the absorber, we can find our lean amine and rich amine. F2 it will be the recycled lean amine, and F3 it will be the rich amine. Applying a mole balance for the amine, it will be very low percentage, and this is because it can affect the trace inside the absorber, so it should be at very low percentage with a good absorbing rate, which is in our case it can absorb up to 50% of the CO2, and the remaining 48% it will be water. And if we apply the material balance, mole balance on the stripper, we already got our unknowns, which they are F3, which is the rich amine entering the stripper, and then we have F2, which is recycled lean amine, and then F4, which is CO2 gas.
Assalamu alaikum and hello everyone, I'm Nabila, and in this video I will be talking about adsorption process. In hydrogen production process, the last step will be adsorption, which is used to purify and enrich hydrogen before it goes out. For the overview of this whole video, I will be talking about types of adsorbent, adsorption isotherm, and scale up, which involve breakthrough curve, adsorption tower design, PSA process, and scale up calculation. Before designing an adsorption process, the first step is to select the type of adsorbent. Some factors that need to be considered when selecting adsorbent are high selectivity, high working capacity, and has strong desorption capability. In this table, you can see several mainly used types of adsorbents such as activated carbon, 5A molecular sieve, and 13S molecular sieve. This adsorbent has their own advantages and disadvantages. Moving on to the next part, the adsorption isotherm. Adsorption isotherm is a curve relating the equilibrium concentration of a solid on the surface of an adsorbent QE to the concentration of the solid in the liquid CE. The adsorption isotherm is also known as equation relating the amount of solid adsorbed onto the solid and the equilibrium concentration of the solid in solution at a given temperature. The relationship between QE and CE can normally be fitted into one or more equilibrium isotherm models. We have two types of isotherm models that are commonly used, which is Langmuir and Friendly. Langmuir has several assumptions, which are uniform surface, monolayered adsorption, and dynamic equilibrium between adsorbed and free molecules. And for Friendly, it is for multi-site adsorption and it represents isothermal variation of gas quantity adsorbed by unit mass solid adsorbent with pressure. Both Langmuir and Friendly is used for chemabsorption and physorption. After calculating the data based on the journals, linear graphs are obtained. After correlating the adsorption equilibrium data with Langmuir equation, this isotherm is chosen because it gives the highest R-squared value in the linear graph compared to Friendly isotherm. The first graph shows Langmuir isotherm of 13S molecular sieve, which gives R-squared value of 1, and the second graph shows Langmuir isotherm of activated carbon, which gives R-squared value of 0.9995. Moving on to the next point, breakthrough curve. A breakthrough curve shows the ratio of the outlet concentration and the influent concentration against the contact time at an atmospheric pressure and at a temperature. The mass transfer zone MTZ in a packed bed system is defined as the zone of the packed column where the active adsorption happens. Since all three adsorbents have the highest equilibrium adsorption for carbon dioxide, the breakthrough curve for carbon dioxide is analyzed. To calculate MTZ from the graph, values of Du can be obtained when C per C naught is equal to 0.01 and Tt can be obtained when C per C naught is equal to 0.5. From the graph, activated carbon adsorbent bed with total height of 1 meter will give MTZ of 0.48 meter and 13S molecular sieve with total height of 7.3 meter will give MTZ value of 2.48. This shows that zeolite 13S has longer saturation times since it has larger pore volume compared to other adsorbents. The breakthrough time of an activated carbon is shorter compared to molecular sieve 13S because it has lower adsorption capacity. For the adsorption tower design, we will use two towers, which the first one will be in adsorption mode and another will be in desorption mode at the same time. According to adsorption capacity of activated carbon and molecular sieve, the only difference is in methane and carbon monoxide arrangement. Hence, combining both of these adsorbents will have higher dispersion efficiency for each molecule. The steps of purification for PSA process starts with adsorption and providing purge, where the first bed is used in adsorption mode, while the other will be used for regeneration step. Then equalization depressurization and equalization pressurization step, which is when the first bed will be depressurized and another is pressurized. Next, the pressurizing step, which is when the bed is pressurized with inlet feed. And finally, the regeneration step, where the pressure is reduced to atmospheric pressure and purged by a fraction of product. To produce at least 30,000 tons per year of hydrogen gas, a scale-up calculation is needed. The proposed exhaustion tower is using SA system with 2 towers in total, and each column is layered with 13S molecular sieve and activated carbon. New total height of 10.97 and new breakpoint time of 44.05 minutes is obtained. This exhaustion tower will produce at least total production of 30,243 tons per year of hydrogen gas.
This incubator project requires us to utilize all the 3 subjects we are taking this semester. We felt that this project was very interesting, and most importantly, it motivates us to learn deeper and let us have a glance into real-life industry. By designing this project, we obtained the chance to generate broad array of possible alternative points of view to a single problem. This object was also able to utilize the expertise of each member to together come out with a design. Throughout the project designing, we experienced a slight rush due to our horrible time management, and luckily we are able to overcome it. Furthermore, by studying books and doing researches out of the textbooks, we are able to gain more than we could by just studying in class. And without doubt, those we gain are something precious and definitely be useful for our future life. As conclusion, it was a fun journey and things might get easier if our group time management and also the cooperation between us was better. In future, more meetings will be conducted either online or offline to deal with this situation.